Hi, I hope you're doing good. I'm Paymo, and I'm going to present our paper, The Master Key Filters Hypothesis, for AAAI conference in 2025. Our paper is about analyzing and understanding generalization in CNNs and DSCNNs, specifically in their convolutional filters. Before this paper, I personally thought that generalization only takes place in the first layers of CNNs, and the deeper we go, the filters gets more specific and more specialized, capturing more conceptual and hard to understand things for that specific data set. But in this paper, we're going to present to you that that might not be the case. To give you some background information about this widely accepted notion that degeneralization takes place in the first layers, I have to introduce you to the paper How Transferable Are Features in Deep Neural Networks by Usinski. I have to mention that I had the honor to personally meet Usinski and discuss our paper with him. And if you're interested in understanding CNS, I highly recommend reading his whole stuff. They're really in depth. The paper starts with this argument that we know that the first layers are Gabor filters, so they must be general, and the last layer must be specific. So, as you can see in green, it argues that there must be a transition phase between these general filters at the start and that specific layer. And it comes with a clever experiment to show that. It trains two models, one on a data set and one on a different data set. In this case, data set A that I'm referring to is ImageNet data sets, only the images that contains human-made stuff. For example, chairs, tables, spoons. And dataset B is only images in ImageNet dataset that is natural images, dogs, cats, trees. So it trains model A on dataset A, trains model B on dataset B, and it transfers for example, the first three layer of the model A to the model B, and it freezes those. And the other layers are trainable, and it trains on that the other data set. For example, it trains the model A on human-made stuff. It transfers the filters to model B and trains the model B on natural images. And with this, it comes up with this chart. So the more layers we're adding and freezing, there's an accuracy drop. And if we transfer all of the layers to the last point, so the only trainable layer is that last MLP layer, there's a huge drop. It's about like 25% drop. So this paper conclude that because we can see this dropping trend, so filters must get special as we go deeper. I should add this, that if we accept that this is an essential property of our model, that the deeper, the more specialized filters should be, we have to conclude two things. First, the deeper our model is, the more layers it has. We should expect more of these specialized filters. And I think this is obvious. The second one is the higher accuracy our model gets, the more of these specialized filters we should expect. It is because if we accept that this is the nature of deep learning, so the higher accuracy model suggests that it gets closer to its nature. So it should converge better to those specialized filters that it is supposed to converge. And another background I have to give you is our previous paper, Unveiling the Unseen. We analyzed the filters of DSCNNs and we conclude that there's a pattern in those. Here, is some random filters of DSCNN models, and these are classical CNNs. We cannot find any clear pattern in classical CNNs, but in DSCNNs, you can observe there are some patterns. And we tried to classify these. We classified into 8 groups, and interestingly, all of them are related to Gaussian functions. This was our observation. We plotted some random samples from two different architectures, the SCNN architecture, from first layer, middle layer, and last layer. And as you can see, these are pretty similar, and the patterns look alike. The first layer is better converged, but the other two layers look very similar. The question is, how can one be general and how can one be special? This was a little bit bugging and in contrast to what we thought before. So we had to repeat Usinski's experiments with DSCNN models. For repeating Usinski experiment with DSCNNs, we splitted images exactly like he did into human-made images and natural images. And for transferring and freezing, we only transferred the convolutional part of the DSCNNs because DSCNNs has an MLP layer after the convolutional that is learnable. So we repeated Usinski experiment with DSCNNs, and as you can see, there's no drop. We had some more experiments too. For example, we tried to, after not only transferring and freezing all of the convolutional filters, we shuffled those. We only, for example, transferred the first three layers and repeated those to fill out all of the filters. We tried to like reverse all of the filters. In none of those experiments, we observed a like tangible drop in accuracy. But there's a question why our observation is different at Yusinevsky. Is it because we're experimenting on DSCNN architecture or CNNs different? So we had to experiment with CNNs too. So we repeated Yusinski experiment with ResNets, which is a classical CNN. And as you can see, there's not much drop. Actually, it maintained 92.5% of its original accuracy. And if you go higher ResNets, the drop will be less. This is in contradiction still with Yusinski's observation. Why is that? If you go and check out the code Yusinski implemented for that model, there's no residual connection. So can this be because of residual connections? And the answer is no. Just for a recap, if we accept the notion that later filters are more specialized as a characteristic of our CNN models is true, there's two things. The deeper the model is, it should be more specialized, and the higher the accuracy, the better specialized filters we have to observe. Here is that experiment for ResNets. The x-axis is their original accuracy on natural images of ImageNet. So if it is like 80%, it means that if you train it on natural part of ImageNet, it achieves 80% accuracy. The y-axis is if we train that model on human-made, if we transfer all of the filters to the model and freeze them and only train the last MLP layer, how much accuracy in percentage does it retain? This means that if something is 50% in y-axis, it means that the accuracy dropped for half. And as you can see, there's a trend in the chart. The higher original accuracy we get, the higher accuracy retaining will be. The accuracy retaining is almost close to 95%. So this suggests that if we would have a model with more than 95, 98% original accuracy, the trend suggests that we may even get close to 100% accuracy retaining. And this is also suggesting that the less accuracy we have, the less accuracy retaining will be. So we're getting closer and closer to Usinski's model. We can show the exact same charts with another x-axis, which is number of layers. And you can see the overall trend too. Here we can conclude that our results are different from Usinski's result because his model was old and lower in accuracy, and our models are higher in accuracy. But the question is why higher accuracy models are getting more general and not more specialized. Our answer is the master key filters hypothesis. So we hypothesize that there exist master key filter sets that are general for visual data. And the depth-wise filters in DSCNNs tends to converge to these master key filters, regardless of a specific dataset, task, or architecture. We have some experiments to back up our hypothesis. First, regardless of a specific dataset. Assume that our hypothesis is true. So if we have different data sets and we train our model in a bigger data set and we transfer the filters in another model and we freeze that and we train it on another data set which is smaller, we should expect to see some increase in accuracy. Why? Because that bigger model, the filters tend to converge better to that optimal point. So it will help the other model. And this is exactly what we observed. Here, the data sets are sorted by the size, and these are some pretty different and unrelated data set. For example, pets, flowers, and foods. But as you can see, if we train something in a bigger data set and we transfer it even in an unrelated data set, the accuracy will increase. Here you can see a plus trend, and in the upper triangle, you can see a negative trend. But we even hypothesized that this is regardless of architecture. So we have two architectures, Comnex and Hornet. They're very different in architecture, and the only similarity is that they're using some depth-wise filters in those models. So we trained Hornets on foods, and we transferred all of the filters to Convnex, and we froze them. And we trained Convnex on pets, and the accuracy increased by 3%. It was a hard presentation for me. This is the QR code of our paper, and if you had any suggestions or questions, I'm glad to see your email. So peace and goodbye.